Today I have to talk about the three aspects related with the welding, and these are basically related with the electron beam welding. This is the first, and then one issue or the difficulty encountered during the DC welding is the direct current arc welding. That is called arc blow. So the reasons behind this arc blow and the remedy and how to overcome this arc blow, about that we'll be talking. And the lastly I will try to talk about the welding defects. We call them as weld discontinuities also. There is a little difference in the two. Like when the weld joint is rejected, then we call that the defect is of the large size, and it needs the joint needs to be replaced, or it has to be rejected. The discontinuities are also like the undesirable features which may be acceptable, may not be acceptable. So the weld discontinuities, when they are unacceptable, we call them as a defect. If they are acceptable, then those are undesirable features but still acceptable. So this has a much wider umbrella. Both acceptable and non-acceptable discontinuities are possible in a weld joint. So what are those the discontinuities? About that we'll be talking. So basically the causes, mechanisms, and the remedy of these the discontinuities, that is what we'll try to talk about. So going through the first one, this is the electron beam welding. So this is basically the high power density process, matching with the laser beam welding. So like say it's very common to go up to, like say, 10 to the power 8 to 10 to the power 10 watt per mm square, kind of the power density which is possible. So you know that whenever the power density, high power density is available with the welding process, for fusion of the fine surfaces to develop the joint, you see, it requires the less heat input for facilitating the fusion, which may be as low as, like say, 0.2 kilojoule per mm of the weld line which is to be joined. Otherwise, normally say it goes up to 10 to the power 1 to 5 kilojoule also, so which is significantly high. And that is why high power density electron beam welding process is basically low heat input process, which means when you develop a weld joint like this, so a very small weld size, weld width is achieved, which may be, like say, 500 micrometer, okay, or 1000 micrometer. It's in mm, 1 mm. So the weld is very narrow. Okay, this is one thing, and because of this narrow width of the weld, you see, the welding and fusion related issues are minimized. At the same time, due to the low heat input, what you have, very narrow heat affected zone, means the metallurgical and mechanical property variation in the base metal away from the fusion boundary are very less. So the heat affected zone is also very low. And the third aspect, very important aspect, that most of the time electron beam welding is performed in a vacuum only. So this is the approach of providing the shielding to the weld metal. So since it needs vacuum, so obviously you need a chamber. See, so here it may be connected to the vacuum pump, and here you have on the table, and over the table you mount the workpiece to be joined. Okay, like this. This is the workpiece table. So now obviously the entire assembly has to be placed in the enclosed chamber, so that you have the desired vacuum, maybe of 10 to the power minus 3 to 10 to the power minus 5 torque kind of thing. Okay, now here only you have the laser electron beam gun. Okay, you can say this in a simplified form as a electron beam gun, which will be generating the electron beam. This beam is focused over the surface of the workpiece, and there high velocity moving electrons impacting the surface of workpiece, generating the heat and facilitating the melting, generating the high power density. Since the electrons are very light, and when they are directed towards the surface of workpiece, if these moving electrons are directed to the workpiece in the ambient environment, like say where you have air, oxygen and nitrogen, so the light, very small size, high velocity moving electrons impacting with the other gaseous molecules will be losing their kinetic energy, and so they may not be able to generate enough heat, they may not be able to melt the base metal, so for the welding purpose. So it is important that high velocity moving electrons are directed to the surface of workpiece without loss of any kinetic energy of the high velocity moving electrons. Okay, so when these impact, these electrons will be impacting, they will be generating enough heat for facilitating the fusion. Okay, that this is why we have to carry out the electron beam welding or electron beam machining in vacuum only, so that there is no loss of the energy of the electrons when they are directed towards the surface of the workpiece, either for machining or for welding purpose. Okay, in case of machining, we basically carry out the sublimation or evaporation of the metal, so metal is directly converted into the vapors. There is no melting as such, because of the high power density that is realized during using this electron beam welding. It helps to evaporate, so the controlled removal of the metal from the workpiece will be leading to the machining, and here we just want the fusion, so the power density is somewhat less, and so that melting takes place rather than evaporation. Is still low melting point metals, low boiling point metals like zinc or magnesium, they will be evaporating also because of the high power density and high temperature, which is generated around like 25 to 30 degrees centigrade, 30,000 degrees centigrade or so. Okay, so the another so the third aspect, you see, apart from the high kinetic, high power density leading to the low heat input, leading to the narrow weld zone and narrow heat affected zone, so your there are so many things which are what happened. Okay, so there are so many positive sides of as far as the electron beam welding is concerned. Like one, I said it's very low heat input because of the high power density process, leading to the very narrow HOZ and the weld sizes, and because of this your reduced issues related to the heat input, because you are providing very less heat. The second aspect is that you can because of the high power density, very localized heating, you can really achieve the very deep penetration, and therefore like say 200 to 300 thick plates or blocks can be welded using these electron beams. So ranging starts at 25 to 300 thick sheets can be welded because of its capability to deliver high power density. And the third aspect, we use basically vacuum for EBM is carried out in EBW, electron welding is carried out in vacuum. So there is no oxygen, there is no nitrogen in the weld environment, and that's why you get very clean weld. Okay, so you know that if we are using very low heat and very clean weld is produced, then the quality of the electron beam weld is very good. Okay, so even this is far better than the TIG welding. TIG offers one of the cleanest and the best quality weld among the arc welding processes. But among the all kind of the welding processes, whether they are all types of the fusion welding processes, among all fusion welding processes, probably the electron beam welding is the best one in terms of the quality, in terms of the heat need to be supplied, and in terms of the cleanliness of the weld. Okay, so because of this is used for extremely critical applications, like say you have to develop the nuclear reactor weld joints, aircraft components, or aerospace or spacecraft components. So when very critical components need to be joined for critical applications where there is a huge risk of life, huge risk of the property in case of the failure, so those are done or welded using the electron beam. One more additional application of the electron beam welding is joining of the dissimilar metals, like metal A is welded with the metal B, and A and B both have no compatibility with each other whatsoever in terms of the physical properties, in terms of mechanical properties or chemical properties. When such kind of the metals are joined by fusion welding, normally they create a lot of problems. But when electron beam welding is performed, it can be done with reasonably good welding. Okay, reasonably good weld quality can be achieved using electron beam welding. Still there is a fusion, but the fusion is very controlled as per the need. For example, let's take this one. A and B are not compatible, so if you can fuse 10% of A and 90% of the B as per your need, or you can do otherwise. You can decide the portion of the A or B need to be moved, because you have got very good control over the location where beam can be directed, so that you can achieve the desired melting of a particular base metal, desired amount of melting of the base metal, desired quantity. Okay, so this was all about the electron beam welding. This is really very good welding process because of the high power density. It offers very good quality weld in vacuum environment. Okay, that was about the electron beam welding. Let me talk about the arc blow. Okay, so you know that in welding current, in welding arc welding processes, say this is the welding arc, right? So in base metal, and here your the fusion is taking place like this. This is the power source. Okay, say DC, so the negative terminal is connected to the electrode, and say positive terminal is connected to the workpiece like this. Okay, so when you have the things in the vertical position, this axis of the electrode is almost 90 degree. Okay, but usually what we do, axis of electrode may vary, like say 45 to 60 degree when we are performing the manual metal arc welding. This may be true for TIG welding kind of case. So what's happening, like when the electrode moves towards the sides here, say this is the arc location, so around the arc you are having certain things, like what is the flow of current, negative terminal to the electrode, then the current is flowing like this. Arc is nothing, just it's just like flow of electrons and ions. Electrons constitutes to the 99% of the welding current, and maybe 1% is going for the ion, caused by the ion current. So electron current and ion current, that's how. And then these electrons will be moving through the base metal to complete the circuit like this. Okay, so you know that, say if the welding current I is flowing around the electrode, there will be a kind of electromagnetic field which will be induced, that will be generated. So wherever the current is flowing, you will see that there is an electromagnetic field. Okay, so when you see the electromagnetic field due to the flow of current through the base metal, electromagnetic field due to the flow of current through the arc. Okay, so what will be happening? The electromagnetic field EMF generated due to the flow of current through the arc and EMF being generated due to the flow of current through the base metal. When these two start interacting with each other, they either attract or repel. Okay, so let's take a situation where this is the arc, this is how the current is flowing, this is the power source. Okay, so this is the arc axis. Okay, so arc is expected to move along the axis of the electrode. Okay, so there will be electromagnetic field all around the arc, and the current is flowing like this. This is the positive terminal and negative terminal, so the flow of current is taking place. So when there will be electromagnetic field around the base metal as well. When the two electromagnetic fields interact with each other, they will, depending on the flow of current, they will either repel or attract. Okay, so when this is happening, so since the arc is basically the flow of electrons, flow of current, and around that you have the electromagnetic field. So because of this either attraction or repulsion, the flow of the electrons is affected. So the flow of electrons, when it is affected, like it can, due to the repelling, it may move like this, or due to attraction it may move like this. So both are the kind of situations which are created. Okay, so basically in both the cases what we are having, the welding arc is not moving in the direction of the, or in the axis of the electrode, but either it is deflected one side or other. Okay, so if the welding direction, if this is the welding direction, then arc will be moving ahead of the electrode position, or in other case the electrode will be moving backward side. So in one case it is forward the deflection, and another case it is backward deflection. Okay, and this simply depends on the direction in which the welding is being done, or the heat source is being moved. Okay, so let's say here this is the arc. Due to the deflection, arc is moving this to this location. So if the welding, this is the already welded section, and this is the section yet to be welded. So this is an example of the forward arc flow. If the arc is deflecting backside, then arc will be directed towards the already welded section. Okay, in backward arc blow. Okay, so the arc blow is what? It is just the deflection of arc from its axis. It is not moving in the direction of its axis, but it is deflecting either in forward direction or in backward direction, and that is happening primarily due to the interaction of the electromagnetic fields. Okay, since we are using DC, so the flow of current, the direction of flow of current remains same, its magnitude remains same, so they will keep on interacting with each other. Okay, so the arc blow primarily happening due to the interaction of the electromagnetic fields being generated due to the flow of current through the arc and through the base metal is one thing. Okay, they can attract or they can repel depending upon the ground position or depending on the connection of the welding current. So say yeah, so here let's say this is the base metal, and here you have the arc, okay, the power source. So the negative terminal and positive terminal connected here. Now the base metal you can connect at this location, or you can also connect at this location. What is the difference in the two? Let me explain that. So in one case, when there is a flow of current is taking place after establishing the arc, the connection being made at location 1. Okay, so the flow of current will be happening in this way, because current will try to follow the path of least resistance. When you are having the connection at the location 2, in that case the flow of current will be in this direction. So depending upon this connection of the power source with the base metal, that is known as ground connection, the flow of current through the base metal is affected. It can help or it can resist the arc blow. So sometimes if it is deflecting in one direction, then what we do, we change the ground connection location so that the effect of arc blow is neutralized. Okay, so now as far as the remedy is concerned of controlling the arc blow, since this is the common only in DC, because the direction and magnitude remains constant, so if we switch over to the AC, then arc blow is neutralized, because in every half cycle the direction and magnitude, every half cycle your direction of the current flow will keep on changing. So in half cycle the arc is deflecting in one side, in another half cycle it is deflecting in other side, and that's how it is neutralized. So basically arc blow effect is neutralized, and it is not observed at all in case of the AC. Okay, the second thing that we can do is, arc blow effect is more dominating when the arc length is more. So if the arc length is reduced, then its tendency, the extent of deflection is reduced. So the next aspect is arc length is reduced. Once the arc length is reduced, then the extent of deflection of arc is reduced. Third is, since it is related with the interaction of the electromagnetic field, so if it is possible, then reduce the welding current magnitude. Although this may defeat the purpose of welding itself, because you may not be able to help, you will not be able to melt the base plates up to the desired thickness, so you may not be getting the desired penetration, and you may not be getting the desired welding also. So this may not be a good option. Okay, now there is one more the thing that is about this is the additional aspect, like when you have the arc location here, so the electromagnetic field around the arc will be equally distributed all around, but since here you are having the air and magnetic lines cannot flow through the air, so they start getting segregated here. So this will be causing the arc to deflect in backward side. Okay, if this is the welding direction. So to neutralize this kind of aspect, what we do, we place one metallic piece here. Okay, so now the magnetic lines can start flowing through the steel base additional metal which has been placed touching to the metal plates which are being welded. So because of this equalized distribution of electromagnetic field, there is no localization now. There is no localization of the magnetic field, and so the deflection tendency is reduced. So you can say a block of the steel or the metal is placed adjacent to the plates which are being welded, so that there is more equal distribution of the equal and uniform distribution of the electromagnetic fields all around the arc, and that's how the tendency of the arc deflection or arc blow is reduced. Okay, so this was about those three things. Now the electron beam welding and the arc blow. Okay, now coming down to the third aspect, that was about the weld discontinuities or effects. So there are certain categories of the weld defects and discontinuities. Like say these are like one which is very common, that happens due to the gas presence of the gases in the gases in the weld metal. So when like say you have produced the molten metal, and the atmospheric gases have got dissolved and they could not come out, so they are trapped inside the weld metal, so leading to the pores. The gaseous presence of the gases in the weld metal which were unable to come out of the weld metal due to the rapid solidification, leading to the development of pores. So primarily the problem here is due to the difference in the solid and liquid state solubility of the gases. If the dissolved gases, if the gases get dissolved in equal amount in solid and liquid state, then there is no rejection. Things will not be segregating and they won't be pores. They will get dissolved rather. Okay. So this is one aspect, like the gases, large difference in solubility of the gases in the liquid and solid state. So when they are in the liquid state, they are well dissolved, but when the solidification starts, that too it is happening very fast. So the dissolved gases are not able to come out of the molten metal and they get trapped, and that is leading to the pores or the porosity. Okay. So maybe anything that is reducing that is permitting longer time for the gases to escape from the molten metal, like reduced cooling rate, will be leading to the increased solidification time. So the lot of time will be available for the gases to come out of the molten metal. Okay. So your gas rejection tendency will be increased and porosity will be reduced. So as a correction method, we just clean the surfaces, so there are no impurities, there is no moisture from the electrode, from the gases. Okay. And then maybe if possible you can preheat the plates so that your cooling rate is reduced during the welding. That is reduced cooling rate is increasing the solidification time and the increased tendency for escaping of the gases from the molten metal. Okay. So the porosity tendency is reduced. So this is one very common issue which is common kind of the weld discontinuity, that is the porosity, and this happening due to the presence of the gases in the metal. These gases may come from the number of sources like moisture or presence of impurities at the surface. So we can overcome that to some extent by preheating, so that all moisture and impurities are eliminated, cooling rate is reduced and solidification time is increased. Okay. And in shielded metal arc welding processes, like the electrode having the fluxes absorbs the moisture. So if you go for proper baking of the electrode, say 100 to 150 degrees centigrade, say for 30 minutes, then all moisture will be driven off and you will get very clean the weld free from the gases. Okay. So the porosity is one thing, and it's happening due to the entrapment of the gases in the weld metal due to the rapid solidification. Sorry. So the best way here is to clean the things, preheat the things and remove the moisture, and use clean gases, use clean the base metal, and properly baked electrodes will be helping to eliminate all these gases. Okay. So this is one discontinuity. The second discontinuity, which is very common also, that is inclusions. So in the weld metal you have oxygen and nitrogen. So if the gases, these gases are not just getting dissolved, if they interact chemically with the base metal, like say the metal is interacting with the oxygen, metal is interacting with the nitrogen, so forming their oxides and nitrides. And if these oxides and nitrides which are present in the weld metal, if they are not able to escape, if they are not able to get removed in form of slag, if that is the case, then these oxides and nitrides will be left in the weld metal, and these will be breaking the discontinuity of the metal in the weld zone. So these will be weakening the weld joint, because these will be acting as a stress razor. These do not support the external load, so in general they weaken the base metal. So that is why it is important that all these oxides and nitrides are removed. So how we do, like basically we add the fluxes, so the flux interacts with these impurities to form slag. Slag being lighter floats at the surface. This is the slag that you can remove, you can chip off after the welding, so that a clean weld is achieved and there is no oxide and nitride inclusion in the weld metal. Okay, so this inclusion is the another kind of the weld discontinuity which is happening in presence of the gases which are interacting with the metal, forming their oxides and nitrides, and if these are getting trapped, you get the inclusions. So the remedy is avoid the presence of these gases in the weld metal. So that is happening primarily due to the poor shielding. If that is the poor shielding is there, then these gases will be there in the weld metal, and they will be leading to the increased tendency of the inclusion. So shielding has to be enhanced. These tendencies will not be there with the electron beam welding, where we use vacuum, or tendency is also less in TIG welding, where very firm protection of the inert gases is used. Likewise in plasma arc welding also. So the tendency of these inclusions is reduced if we have proper shielding. Okay, so shielding either from vacuum or from the molten flux, as in case of the electroslag and submerged arc welding, or like say you have inert gas jet in case of like say the MIG welding or TIG welding or plasma arc welding. So that shielding is somewhat poor in case of shielded metal arc welding, where inactive gas environment is produced all around the. So in SMAW, your flux decomposes and forms the inactive gases. It's the protection is there, but it's not as good as in case of the inert gas jet or vacuum kind of thing. Okay, so this is about the inclusion. So whatever your arc welding process, use the proper shielding through the proper flow rate of the gases, or use proper flux so that the impurities form slag and they are removed. Okay, so this was the second one, and the third one, which is very common, is cracking. Okay, so now there are multiple types of the cracking. Let us understand this based on the conditions in which the cracks are made, cracks are developed, and the location where these develop. Okay, these are the two broad classifications. So under the conditions, like so there is a hot crack, this is also known as solidification crack. This happens just at the end of the welding. Solidification crack. Okay, so near the end of the welding, when you as soon as you complete the weld, you will see that cracks are there. And another is cold crack. So this cold crack happens like say within 30 minutes, or after 2 days, or after 15 days, like this. So this happens under the very normal ambient temperature conditions or even low temperature conditions. That's why these are called cold crack. As far as location is concerned, based on the location, say this is the top view of the weld. Okay, so depending upon the location and orientation of these, if we see this weld in the front view, it will look like this. Okay, so this is the top view and this is the front view, right? So now you can have the crack at the center line like this. Crack is here. So weld center line crack, and this is most common solidification crack which is observed in the weld metal. Solidification crack, it's like, although it's a particular condition dependent, but here this solidification crack occurs at the center line. So weld center line crack is basically solidification crack. This is one. Then you can have the crack at the just near at the end of at the fusion boundary. Okay, this is the fusion boundary, this is the weld. Okay, so fusion boundary crack will be here. Okay, so this you can say as under bead crack, UBC, under bead crack. This is under bead crack. Since this is happening in the direction of the axis of the weld, this is the weld axis. Okay, so we call all such cracks which are in line with the axis of the weld, they are called longitudinal weld. Okay, if the cracks are occurring perpendicular to the welding direction like this, then we call them as a transverse cracks. Okay, transverse cracks. If the crack is happening at the location where your weld has ended, say this is the last location of the weld, here you find lot of cracks, so that will be the location of crater crack. Okay, So under bead crack, just below the bead, okay, the cracks in parallel to the welding axis, that is called longitudinal crack. Cracks perpendicular to the axis of the weld, they are called transverse crack. Cracks located at the crater location, they are termed as crater crack. Okay. Then there is a few more types of the cracks, like say you have your weld bead and this is the weld joint. Okay, so you can get the crack here. This is the welded toe, weld toe crack. Okay. Now cracks can be there at the root, so you can call it as a root crack. So this is what you can say, that depending upon the condition in which crack is formed and the location where these are formed, you have the different types of crack. As far as the cold crack is concerned, the cold cracks are mostly developed in the heat affected zone, HAZ, and also in the weld. Okay. So these can be transverse cracks, these can be longitudinal cracks, but these are mostly in the HAZ of steels or in the weld metal as well. Okay, so that was about the cracking. Now coming to the causes, I'll talk primarily about the two types of the cracks: hot crack, or you can say solidification crack, and cold crack. Okay, cold cracking. So the solidification cracks happen primarily due to the presence of low melting point impurities in the weld metal. Like you have lead, you have got sulfur, you have got phosphorus. So these elements form the very low melting point constituents, and these low melting point constituents segregate at the weld center. So your base weld metal has solidified at 1400 degrees centigrade. The weld metal center is still having something to solidify at 700 degrees centigrade. So what is happening? Everything has got solidified and it is shrinking at the in the weld zone, also in the heat affected zone. So if the shrinkage is taking place, that will be developing the tensile residual stresses. So in presence of tensile residual stresses coupled with the low melting point metal, okay, at the weld center, your simply cracks get open like this at the weld center. So the hot cracks happening near the end of the weld solidification, when the metal is still hot. Okay, so the weld metal, most of the weld metal has already got solidified and it has shrink up to 700 degrees centigrade from 1400 during the cooling, but still at the weld center you have something is still left to solidify, and wherever it is left, there you will see cracks. So the best remedy to avoid these cracks in especially steel welding is addition of the manganese. So the manganese takes care of the formation of the low melting point constituents like iron sulfide formation. So sulfur and this problem is more pronounced in austenitic stainless steel welding. So their addition of the manganese, their addition of some ferritic fillers that helps as that acts as a you can say sink or storage for phosphorus and the sulfur kind of impurities. So it absorbs basically, but there is no remedy for the lead. Lead is mostly added in the free machining steels. And if it is there in large quantity, you cannot do anything, but there will be cracks. So we basically avoid the welding of free machining steels, because presence of lead and high amount of the sulfur in free machining steels makes the steel very crack sensitive, hot crack sensitive. So we just avoid the welding of the low melting point, avoid the welding of the free machining steels or the steels having the high percentage of sulfur, phosphorus. Usually we limit the sulfur and phosphorus in steels below the 0.05%. If the steel is having more than 0.05, then it will become crack sensitive, and we would like to avoid that situation. Okay, so we want that the sulfur and phosphorus content in steel is maintained below 0.05, otherwise it will become very crack sensitive. Coming to the cold cracking. Okay, cold cracking is caused by three situations, like there is a lot of hydrogen left in weld, okay, and there is a high tensile residual stress, TRS, tensile residual stress development in the weld zone, and the formation of very hard and brittle constituents in the weld zone like the martensite. Okay, so when these when a cocktail of the three deadly things happen, especially in steels, hardenable steels, which are like say the steels having 0.3 or more percentage of carbons. When this happens, the steel when of this kind is welded, you will find that due to the presence of moisture, there is always some amount of hydrogen, and due to the differential heating and cooling, there is always some kind of tensile residual stress. And when it is coupled with the high carbon content or high carbon equivalent like high Ce greater than 0.3, you will find that there is some amount of the martensite formation in the weld as well as heat affected zone. So invariably, you in a steel welding of the hardenable steels, you have the hydrogen if improper welding is carried out without taking proper care of the moisture or the organic compounds like oil, paint, etc. from the surface of the base metal. The TRS, tensile residual stresses, are invariably present if there is no proper preheat, or the hard and brittle martensite formation is also there with the hardenable steels if there is no proper preheat. Okay, so all these are usually present if there is no preheat. Okay, there is no proper cleaning, and in that case, the hydrogen coupled with the tensile residual stresses and the brittle structure invariably forms the crack in the heat affected zone and the weld metal. So these things happen especially at the low temperature, and it takes little longer time. That's why it is called cold crack or delayed crack. It doesn't happen immediately after the welding. It may take maybe 24 hours, maybe 7 weeks, maybe 15 days, maybe 6 months. So that's why we call it as a delayed crack as well. And it's happening primarily due to the hydrogen, tensile residual stress, and hard and brittle martensite transformation. So what we can do? One simple remedy is do proper cleaning. This is one. You see, use the proper preheat. So preheating is done, your cooling rate is reduced. Cooling rate is reduced, martensite formation is reduced. Your tensile residual stresses are reduced, and because of the reduced cooling rate, your the hydrogen diffusion is increased, so the hydrogen content in the weld and the heat affected zone is also reduced. So basically all three factors which are contributing towards the cold cracking, that is reduced if we use preheat. So depending upon the Ce, say for carbon equivalent of 0.3, you see little preheat of 50 degrees centigrade will be fine. If it is 0.3 to say 0.5, maybe 100 or 150 degrees centigrade preheat will be okay. If it is more than say 0.5, then you see you need lot of preheat like say 200 degrees centigrade in order to avoid formation of martensite, reduce the tensile residual stresses, and reduce the diffused hydrogen content in the weld. Okay, so the preheating is probably the one of the best alternative to reduce the cold cracking. Third aspect is use such kind of the fillers which will not cause much of the tensile residual stresses, which will absorb the hydrogen. Okay, And so the problem related to the hydrogen and martensitic transformation and tensile resolution, that is reduced, and that happens if we use the filler metal like austenitic stainless steel, if we use the fillers like nickel alloy. So both are softer, they don't cause much issues like the martensitic transformation, and they reduce the tensile resistance, they act as a sink for the hydrogen, so the tendency for cracking is minimized. Okay, so this was another type of cracking. Okay, another type of next weld discontinuity about which I would like to talk is like when we use lack of proper welding parameters. This is very interesting. So if you know that for a given thickness of 10 mm welding, you need 10 mm thick plate welding in a single pass like this. Okay, like this. If you need to supply minimum 1.5 kilojoule per mm, okay, and that you are realizing through the proper welding and the current voltage setting. If your current and voltage setting and the welding speed applied is not corresponding to this one that you should have for melting up to the desired depth through the thickness, if this combination of the welding current and speed, welding current, voltage and speed combination is not corresponding to this much minimum heat supplied for through thickness penetration, then what will be happening? You will not be getting the through thickness penetration. What will be getting? Your penetration is limited. You see, this is the this is the left out portion which has not been melted. So you will find a lot of unwelded section. This is called the defect of lack of penetration, and happening because you did not supply the desired heat. Either your the current was less, instead of say desired current setting of 200, you set it incorrectly at 150, or instead of using the 50 mm per minute welding speed, you use 80 mm per. So higher welding speed or lower current, lower arc voltages will be leading to the reduced heat input. If heat input has been reduced, your penetration will be reduced. Okay, so the lack of penetration is one type of the defect where the heat input is not sufficient. Okay, now the next one is the lack of fusion. This is also due to the less heat input that we are supplying for the welding purpose. Okay, so in that case what happens, say this is how you have prepared the edges of the components to be welded, and you are supplying the heat through the arc. If the welding current is less, if H net is less, it is not less like the desired one to 3.5 kilojoule per mm, if that is the case, then you will find that you are able to deposit the metal in the groove, but there is no melting of the base metal. So if the metal is being just placed and getting solidified without melting of the base metal, so no melting of the base metal, only the metal is being placed and it is getting solidified. So there is no metallic bonding between the two, because for metallic bonding what you need is the melting or fusion of the base and the filler metal, both should mix. Okay, and if we have the no meltings of the base metal situation, then this will be leading to the lack of fusion. Lack of fusion means the base metal surface remains straight and you have just placed the molten metal here. This will simply indicate that there is no fusion of the base metal So this is the kind of defect that is called lack of fusion. Okay, it is different from lack of penetration. In penetration we talk about the depth up to which the base metal has been melted, whether it is complete or it is incomplete. But here you are placing the molten metal without melting the base metal, so that's the lack of heat input. And there will be multiple regions, like over the surface of the base metal you have a thick layer of the rust, thick layer of the oxide which is refractory. Your base metal melting point is just say 550 degrees centigrade, but the rust has been formed, or the oxide layer which has been formed is of 2000 degrees centigrade. melting point. So it is possible that you are not, if you, there has been improper cleaning, no removal of the oxides, no removal of the impurities, then this may not allow the melting of the base metal itself. So that may also lead to the situation of lack of fusion. Okay, so the one case related with the lack of fusion, lack of penetration is that heat input is not proper. Either welding speed is too high or welding current is low. The second case that can lead to the lack of fusion, lack of penetration is improper cleaning. There are impurities, rust, oxides present at the surface interfering with the metal and not permitting the metal to be melted. Okay, the next, the discontinuity that we come across very commonly is the improper weld bead geometry. What is that? We always expect that the weld bead is deposited like this, so the bead angle is low. Okay, so there is no sudden change in cross section. Maybe it is good if it is 10-15 degree bead angle like this, but if the bead is like this, say the metal is deposited like this, so in this case it may be like 100 degree bead angle, 90 degree bead angle. This sudden change in cross section causes the high stress concentration, and high stress concentration frequently causes the cracking or the fracture initiation at the toe of the weld. This is the toe of the weld, this is the bead. Okay, so what you are having basically, the weld and the bead is like this. So the weld is fine, but this section of the base metal and the weld bead will be highly sensitive for stress concentration. So the crack will be initiating from this location only. So high stress concentration at the toe of the weld will be triggering the fracture, will be initiating the crack, and this is particularly due to the improper bead angle. Okay, now the third, you can say the another one is where you have developed the weld bead and it's very rough. Actually, rough means there is a lot of ups and downs in the weld bead, so these will be acting as a lot of stress raisers. These will be acting as a stress raisers and weld discontinuity. Weld discontinuity is basically the rough weld bead or irregular weld bead causing the high stress concentration, leading to the poor the joint strength. Okay, so apart from bead angle, there is one more situation where the bead is not necessary to be of very high height. Like say this is the weld. Okay, so the little reinforcement is fine like this, so this height of the weld above the base metal is called reinforcement. So if this weld reinforcement is this much, this is of no use. Okay, it's not helping. So unnecessary high reinforcement or very peaked bead will not help in any way except in increasing the stress concentration due to the sudden change in cross section. Okay, so you can say the peaked beads or bead of the high stress bead of the high reinforcement, that will not be helpful. That's like another poor weld bead geometry. Another problem is related with the under bead filling. Like say this is the weld, so the weld has not been filled properly. This the weld zone is this. So when you apply tensile load resisting cross sectional area is just this much. So weld will fail in any case from the weld joint. Weld joint will fail from the weld bead only from this location. So this is called underfilling, where weld has not been filled in properly, so it has left some kind of depression in the weld region, leading to the underfilling, causing the reduced cross-sectional area of the weld and a reduced joint strength. Okay, so I think these are all types of these are most common types of the weld discontinuities. This is where probably I will stop, and that's how we have completed our all sections related with the what you call welding.